In this video, we're going to be looking at something called principal ideals. I want to start with a basic definition, and the definition is going to look like this. We're going to let R be a commutative ring. And commutative here is an important part of the definition. And we're going to let A be any element of that ring R. We define the set A inside angle brackets to be equal to the set of things that look like R times A, where R is simply any element of the ring capital R, and because capital R is a commutative ring, this set is also equal to A times R, where R is inside my ring. And some textbooks will write this set as A times R, but we call this set the principal subset of the ring R generated by the element A. Now, it's important to note that I am not requiring that R have a multiplicative identity element. Some textbooks, including the textbook that we're using this summer, do specify that for a principal ideal to be defined, that we have to have R being a commutative ring with a multiplicative identity. So I want to look at the fact that I'm defining a principal subset to be slightly more general than our textbook does. So let me switch some colors and make a note here. If we actually have a ring with identity, so if R is a commutative ring with identity, then it turns out that A will have to belong to the principal subset generated by A. And the reason why is pretty simple. A is going to be equal to 1 times A, and 1 times A is going to be inside the principal subset generated by A by the definition of principal subset. What happens when the ring does not have a multiplicative identity varies. So let's look at that for just a few minutes. If R does not have a multiplicative identity element, then it turns out that we really can't say anything about whether or not A belongs to the principal subset. So we don't know if A belongs to the principal subset generated by A. And I want to kind of look at two examples that illustrate this point. So my first example is going to be, let's let R be the set of even integers under addition and multiplication. Now, we've already know this is a subring of the integers, and we also already know that this particular ring has no multiplicative identity. So I want to simply make a note that we do know that R is a commutative ring without a multiplicative identity element. And I also know that 4 is a perfectly good element of this ring. And so what I want to do is I want to look at the principal subset of 2z generated by 4. Well, that's going to be the set of things that look like 4 times q, where q is drawn from 2z. But I know what that is. In order for q to be in 2z, I know that q is going to be equal to 2 times, let's see, my notation is just a little bit weird there. Q is going to be equal to 2 times something, where that something is pulled from the integers. And this particular thing is an if and only if. So what that means is that this set of objects is really nothing more than 4 times 2k, where k is pulled from the set of integers. And if I think about that, that's going to be the set of 8k's, where k is pulled from the integers. In other words, the principal subset in 2z generated by 4 is going to be the set 0, 8, minus 8, 16, minus 16, 24, minus 24, 32, minus 32, and so on. And it's quite clear that 4 is not inside that set. So this is an example where the element 4 would not be included in the principal subset generated by 4, since our ring is equal to 2z, and there is no 1 inside this ring. But I do also want to look at a second case. So let's look at another example. This time I want to let R be the set 0, 2, 4, 6, 8, 10. And I want to think about this as a subset of Z12. And it is easy enough to use the subring criteria to show that R is a subring of Z12. So it is easy enough to show that R is a subring of Z12. And so I know that R is a commutative ring. Now, what I want to look at is whether or not does R have a multiplicative identity element. So does R have a multiplicative identity? Well, the easiest way of figuring that out is to look at the multiplicative table for this particular ring. I would encourage you to stop the video and make that multiplication table for yourself and answer this question. And when you think you have an answer, turn the video back on. Hopefully you did that. Here's my multiplication table. And if you look at this particular multiplication table, it's pretty clear that R has no multiplicative identity element. There is no element in this list that when you multiply it by everybody in that list that you get that particular element back. If we had a multiplicative identity, then one of these rows would be 0, 2, 4, 6, 8, and 10, and none of them are. Now, what I want to do is I want to look at the principal subset generated by 4 inside this ring R. Well, let's see. The principal subset generated by 4 is going to be anything in R times 4, where R is pulled from that ring. Well, that's going to actually be a nice finite set. This is going to be 0 times 4, 2 times 4, 4 times 4, 6 times 4, 8 times 4, 10 times 4, where all of our answers are reduced modulo 12. And when we do that, we get the set 0, let's see, we get 8, 16 reduces down to 4 mod 12, then we get 24, which reduces down to 0 mod 12, 32 reduces down to 8 mod 12, and 40 reduces down to 4 mod 12, and gee, here's a bunch of repeats, and in set brace notation, we don't have to keep the repeats around. The set 084084 is the same as the set containing 0, 4, and 8, and obviously 4 belongs to this principal subset generated by 4 inside this particular ring. And so there we have an example of a principal subset inside of a commutative ring without a multiplicative identity that contains the generator of the principal subset. The last thing that I want to do in this video is I want to go through a really important, major, but easy to prove theorem. If we let R be a commutative ring, and A is an element of R, then it turns out that the principal subset generated by A is actually an ideal of R. And as a notational note, we usually refer to the principal subset generated by A. We call this guy a principal, let me clean up my writing there, a principal ideal of the ring R. And here's the proof of our theorem. The proof is not very hard, and I actually would encourage you to stop the video, try and prove this for yourself, then start the video and compare it to my proof. Hopefully you did that. To show that this set is an ideal inside R, we need to show the following. We need to say that if I take two elements inside this set, inside the set generated by A, then their difference belongs to that set generated by A. And if we let X be some element of the set generated by A, and R is just any element inside the ring R, we need to show that R times X, which is going to be equal to X times R because the ring is commutative, we have to show that that element also belongs to our subset. Neither one of these is very difficult. So let's get started. Let's let X and Y be inside the set generated by A, and we're going to let R be any element of R. Then we have the following things. X can be written as R1 times A, and Y can be written as R2 times A, where what I know is that R1 and R2 both belong to the ring R. And this is by the definition of principal subset generated by A. Well, that means it's real easy to compute X minus Y. X minus Y is R1A minus R2A. We have the distributive law, which gives us that this can be rewritten as product R1 minus R2 times A, and this guy is in R, so that puts this element inside the subset generated by A by the definition of the principal subset generated by A. Well, we also have this. If I look at R times X, that's going to be R times R1 times A, but I can reassociate this and rewrite it as R times R1 times A, and this element here is inside R, and that puts this element inside the principal subset generated by A, again by the definition of principal subset generated by A. And these two properties that we've just done say that this particular subset generated by A is in fact an ideal of our of our ring R.